Bismillahirrahmanirrahim. Welcome to Transistors and Application series. As you can see that I had already right here. That is our topic today. That is the maximum transistor rating. Our major topics about the working principle of the bipolar junction transistor, how it works, major terms are already covered. Now we are covering the minor course of our bipolar junction transistor series. And these topics are not very important as compared to the previous episode. If you have any problem with the previous episode, I recommend you to first of all clear your basic conceptual questions with us on our Facebook page. You can frequently ask questions over here, our Facebook page, inbox us, and we will reply you. Anyway, these are the minor terms, and you can easily understand after learning the basic concepts of the bipolar junction transistor. And this, by the way, this is maybe the last video of the this format, this handwritten format. Next time maybe we will discuss, because the second portion of the half of this series is covered. Next portion will be started of the applications format, or maybe next time I will also try to show you the transistor data sheets, and that's why we will move towards the computer format or PowerPoint format. So in the episode 11, we are going to have my course outline sheet asks me to solve two examples here, and also maximum transistor ratings. Okay, let's start from the maximum transistor rating. First of all, I want to tell you, any electrical device, definitely have a maximum or a threshold voltage or ratings, power ratings, written on its data sheets on the device or mounted on a device. That any electronic device has a maximum value after which it maybe burns, or it does not works properly, or it may take some extra voltage power. So bipolar junction transistor also has a limitations on its operation called the maximum rating that is available on the data sheets. For example, let's say I already explained many times that if this is a current voltage and this is voltage current, its depletion region is exactly the same of like the normal PN junction diode. If this is a normal PN junction diode, we approximately say that 0.7 volt, and then it's okay. And reverse bias, it's have to block all the current in the reverse direction. This is our expectation, but when we further exceed this and we applied a high voltage, or then its rating, for example, it is designed for 50 volts, and it is even recommended to stay 20% back than the threshold voltage. But let's suppose we cross this 50 volts and we reached to a value that is here, and then it means that, remember that it means that we are crossing these limits and we are going into the breakdown region. This is the breakdown region. Anyway, this is the breakdown region, and if we are going into the breakdown region, then we are crossing the limits, and maybe possibility are this device will not work properly. There are the three basic junctions, these three voltage at collector with respect to base, VCE and VBE, and also IC, collector current, and power dissipation. These are the some terms. This is the power dissipation. This is the power dissipation. Now you can read that this is the power dissipation. Okay, power dissipation, and basically our focus is on the power dissipation. The basic formula for the power is current multiplied with voltage, or you can say that IV, or and voltage multiplied by current. When we talk about the power dissipation, we have to write here in subscript a capital D, which represents the dissipation of the power consumption capacity of the how much power it can bear, this transistor, and this is called the power dissipation. So it is usually the maximum power it can bear or withstand. This is the power dissipation, and that's why it's D written here in the subscript, capital D. Capital basically represents that it is a DC value. Anyway, this is the current and this is the VCE, collector emitter voltage, and this current is of course of collector current, because when we talk about the graph of the output graph, this is the output graph of the bipolar junction transistor, and this is the VCE here we are obtaining, and these output parameters, the graph is between IC and VCE. So current is I, collector current, and voltage is collector emitter voltage. So when we're talking about the ICD rating, and remember that this is a equality sign here, and these are the two product of the two terms. If we want to increase the collector current, we have to decrease the VCE, and if we want to increase VCE, we have to decrease the ICE to balance this. Okay. Furthermore, remember that power if we want to derive a formula for the want to calculate what is the maximum current it can withstand with. For example, this is the maximum current after which it goes into the active region, and usually IC does not increases in ideal case. But let's suppose our IC is increasing, and we want to increase the base current, and then our current this curve will be like here. Then if this is the maximum current that is designed for, we have to definitely calculate the current. If we want to calculate the maximum current, how much it can withstand, definitely IC should be here. This VC goes towards the other side of the equation, it will divide by the power dissipation VCE, and this is the formula for the remember that this is always maximum, and if we want to calculate the formula for VCE goes to the other side, and power dissipation will come here in the denominator. And this is the basics of the maximum transistor rating. And if we want to calculate another term, that is the maximum power dissipation curve, that is another interesting thing. Let me talk about the power dissipation curve. We can plot the collector characteristic curve like these are the collector characteristics curves, and definitely if this is the maximum point, that is called, let's say, A point, and this is the B point, here B point, I'm sorry, remove this is not B point, this is the B point, and by joining these 2 points, this represent that we not have to cross this region, and we not have to go in to upper side, because that this is the maximum current it can withstand. This A to B point shows that the maximum current it can withstand. Then the graph will looks like this, and let's say this is a C point. This shows that the maximum power it can withstand. And here when it is this graph is in y-axis vertically, and it touches the VCE on a point that is called VCE maximum, and this shows that the maximum voltage it can withstand. This VCE is in volts, and this is in milliamperes, and also there is I'll mention that, for example, 10, 20, 30, and I will explain this power dissipation curves when I will taught you about the transistor data sheets in the next episode. And these are these points are available over there. For example, this is 5, 10, 20 volts, and let's say 15, and let's say 18 volts, that's 20 volts, so on. And this is how we can calculate. This is the current, this is the voltage, and this is the combination bit, and this is not nor the x-axis nor the y-axis. So this is the combination here between of the multiplication of I and V. So this is the power, and this portion is usually represented shaded portion here, and this shows that we do not have to go into the shaded portion, we do not have to cross this region, and this is the normal operating region of the power. These are called the power dissipation. This curve is called power dissipation curve, and I will also explain this power dissipation curve in the coming episode. Now the topic is, for example, a certain transistor is to be operated with the VCE. Let's say a certain transistor VCE have 6 volt, this is the VCE, and usually this VCE is maximum VCE, this is the VCE max have 6 volt. Let's say maximum voltage that it can withstand is the 6 volts, and if the its maximum power rating is PD is equals to 250 milliwatt, and what is the maximum or most current it can handle. So we have to calculate the collector current that it can handle this current. So how we can calculate this? This is very simple. Just remember always this formula: power dissipation. When we want to calculate maximum, it is always equals to collector current multiplied by voltage. If we want to calculate, I have explained you the collector current, maximum collector current, then this formula changed like this: power dissipation maximum, this will go into the denominator and the dividend as a dividend, VCE, and IC maximum is equals to power dissipation is 250 into 10 raised to power minus 3. What is the VCE? This is the 6 volt. Then the IC max here available on my sheet is 41.7 milliampere. This is the maximum collector current for this particular value of the VC. Remember that if you want to increase the current that it can handle, this collector current, you want to go upside, you have to go from here towards this side. And if you want to decrease this and increase this voltage, you can decrease this curve will go here. For example, I will show you in the shaded portion. This is the, if you go here in the decrease I collector current and compromise the collector current, this curve will looks like this. It will also go, it will, the benefit is our voltage VCE maximum will increase, and this, if you decrease this will increase, because this is the multiplication I already explained. Now let's talk about another question, and this is available here. You can see that a transistor has the following maximum rating: power dissipation maximum, bipolar junction transistor, NPN simple transistor. Power dissipation maximum is given 0.8 watt. VCE, this is the VCE collector emitter current, voltage, that is the 15 volt maximum volt. This is also maximum, this is maximum, and I collector current, that is maximum it can handle, is 0.1 ampere. Determine that the maximum value of the VCC. What is the maximum biasing current for the collector to this emitter side, and what is, this is a variable source, and we have to calculate that, determine that how much we can what is the maximum rating we can connect this voltage source here and replace this. And remember that we also have to stay within the ratings. There are the two limitations. In the first section we will try to calculate the VCC, and in the second portion of the question we will try to compare and with the power dissipation rating, what we have calculated, what is the provided, and if our power dissipation rating is less than the given, then of course we are in the limits and our VCC is in this safe zone. So let's start. What we need here is the voltage at collector VCC, that is the biasing source for the collector emitter junction, and this is the required here. And remember that this is maximum required, VCC maximum required. And if we can apply this KVL here, then the formula is, or we already derived this formula: VCC is equals to voltage at here, voltage at across this resistance at collector loop plus here VCE. And if we want to calculate VCC maximum, this formula can be modified: voltage across this resistor at collector terminal plus VCE also maximum. What is the VCE maximum? You can see that VCE maximum is the 15 volt. That is given. Now what is VCC max? What is this voltage at resistor RC? Simple, apply the Ohm's law, that is IC RC plus volt. What is the voltage across CE? at collector with respect to emitter, that is maximum, that is 15 volt, and this is given. Now the RC is also known 1 kilo ohm resistance. The question is, what is the collector current? We have to calculate this because if we can calculate this, then when we can further proceed. We here, because this is, we cannot use this maximum current here because this is not a maximum rating. So here we have a formula. We said this is equation number 1, beta DC is equals to IC over IB, and IC can be calculated from this relation beta DC. Rearranging this formula, it becomes IB, and here we have to calculate the IB, applying KVL once again to base loop, base side, and it will becomes when we apply this, I'm using marker here, and I'm writing direct. IB is equals to VBB minus V base emitter divided by RB. What is the VBB? That is 5 volts minus, this is understood 0.7 volts drop, and this is the 22 into 10 raised to power 3. The answer is IB is equals to 195 microampere. We have to substitute this value over here. IC is equals to what is beta DC? That is 100 gain, 100, and 195 microampere, and IC, the answer of the IC is 19.5 milliampere. Now this is the collector current. We have to put this in the value question number 1, so that VCC maximum value we can use is the 19.5 milliampere, and across RC resistor RC, what is the value of 1 kilo, 1 into 10 raised to power 3, and sorry, here this is a plus sign, 15 volts. VCC maximum we can use is the answer is the 34.5 volts. This is answer. This is the first portion we had calculated, that is required. Determine the maximum value to which VCC can be adjusted. The next question portion here is, let's check that is it achievable and within the ratings. How we can calculate? Simply power rating formula. Very simple formula is power dissipation maximum is equals to VCE into IC. Here what is the formula? This is the formula I use. Power dissipation maximum is equals to IC into VCE. Here power VCE is maximum. We can use one term maximum, and definitely second one is the minimum. Now we have to use the power dissipation maximum is equals to, what is the VCE maximum? Here is the given 15 volts. And what is the IC? That is 19.5. I'm using 19.5 milliampere, and the answer for this is 293 milliwatt. And now you can see that 293 milliwatt is less than 800 milliwatt. We can go up, and the maximum power dissipation allowed is the 800 milliwatt, and this is the 293 milliwatt. So we can use this VCC, and it is safe in the safe zone, and this is allowed. This power is allowed. As you can see that in the question, it is said that you can achieve even we can go up to even 0.8 watt, but even this is simply 0.29 watt. So we can say that this is within the ratings. This VCC is now what is the value of VCC? We calculated 34.5 volt is the maximum volt. Okay, take care. We can, the discussion will be continued next time. Watch, learn, grow. Take care. Meet you next time.